is the hottest field in nanophotonics these days. And what it does is, they basically change the phase or amplitude of light dramatically, even with a very thin layer of material. So that's the point. Okay. So this is kind of an intuitive understanding of what Metasurface did. So by the way, if I give you some background, first, metamaterial has been suggested and got highlighted. But people realize that metamaterial must be 3D, so that it's very difficult to create with existing nanofabrication technique. And second, in order to use metamaterial, we want an electromagnetic wave propagate through the metamaterial, but metamaterials are made of metals, right? Metallic structures, so that it's highly absorbing. So practically speaking, light cannot penetrate through the metamaterial that much. So that limits also the practicality of the metamaterials. So people try to do, okay, then if bulk metamaterial is difficult, then probably we can do just a surface. We can just place a, meta atoms on a surface and just use that surface to do something useful. And that's the main idea of having meta surface instead of meta material. And then, so what we can do is, this is called is a lifeguard problem. And, let's say this is a land, and then this is water, sea, and then here's a drawing man. So lifeguard wants to rescue this drawing man, and a drowning man. And drowning man, and so the best way, except let's ignore the wall here. And then what he wants to do is to get to this point, as fast, as soon as possible, right? So that he can, but what you realize is that the swimming speed, of course, is much slower than the speed that he can run. So that based on these two speed, he can basically optimize what would be the optimal path that he can choose to rescue this guy. And that's basically same as the Snell's law, right? The light propagation in medium 1 and medium 2 are different, so that the light actually choose the path that has a minimal action. So this is what happens in a typical situation. And what metamaterial does is like having a wall, very thin but tall, wall of varying heights. Okay, and then the problem becomes a little different, because originally the problem is just these two. One is the incident material, and then relevant with only incident material index and the material 2 index, right? And that's it. That was Snell's law. But now we want to take into account the time that a lifeguard move through this wall. So that's this term. Even though it's extremely thin, but it adds a significant amount of time, so that the entire optimization problem becomes just entirely different. So that now the optimal path is going this way, right? Because the lifeguard wants to minimize the time that he goes through the wall, so that he wants to go this way instead of doing that way, because here the wall is kind of too tall, right? So making Metasurface is kind of designing this wall. Okay, so this wall can be arbitrarily shaped so that we can basically control the propagation of light. Okay, so that's the general idea of things. And how does that relate it with meta atoms? So as you can see here, you can probably learn about the Huygens principle, right? Huygens principle is that in order to describe the propagation of a wave at a wavefront, at each point of a wavefront, you can imagine each point of wavefront can act as a source of a wave, so that you can have a diverging, like a propagating wavefronts from each point on the wave, the previous wavefront, and then these wavefront creates the wavefront at the next moment, and so on, right? And then what metamaterial does is that because these meta atoms have different response to the incident light, so that some of the meta atoms having basically creates the wavefront with a relatively smaller phase shift, but these ones creates wavefronts with a larger phase shift. And if you do so, then even though it's thin and flat, you can basically make your electromagnetic wave to be deflected, right? So that's the key. Like, so the main idea is how to design this thing so that you can manipulate wavefront as you want. So that's the main idea of meta surfaces. So next time, I'm going to tell you a different types of metasurfaces. So it can be, depending on the operation mechanism, it can be resonant tuning, or you can use a geometric phase, or you can do a hybrid, or in terms of a material, it can be plasmonic, or it can be dielectric. And also we sometimes do reflect arrays. So there are many different versions of meta surfaces. And probably, yeah, so I'm probably to this slide as today's final stuff. So the easiest way to create a meta surface is just using a bunch of high index materials, right? And in order to change the effective refractive index, depending on their area fraction. So like, you can think of meta material and meta surface with high index material filling only a small fraction of area, and also think of high index of material filling a large fraction of area. Okay, and in both cases, assuming that the size of an high index structure is much smaller than the wavelength, then of course the effective index of this guy is much smaller than the effective index of that guy, right? Because the volume fraction here is area fraction here is much larger, right? And by doing so, you can basically create whatever effective index that lies in between, n equals 1 to n here, right? By changing basically the area fraction. And if you do so, then you can see here as a function of post diameter. So this is the post diameter. You can achieve the phase difference. So in terms of a transmission amplitude, it's almost 1, but the phase difference increases as you increase the post diameter so that effective index increases, right? It's a very simple technique. It's not even a technique, it's just changing the density basically, okay? And the only interesting feature here is here, where you have a abrupt dip in the transmission spectrum and also a perturbation in the phase. And here what happened is a resonance, right? Even though we try to kind of minimize the resonance, but somehow here the resonance occurred. And then when the resonance occurred, the amplitude and phase of the response changes dramatically. And in this example, this resonance was like unwanted artifact. Okay, people just wanted to use this regime where you can have a nice high transmittance with a large nice variation of the phase, and this was an artifact. And from next time, what we are going to learn is how to actually utilize this resonance. So basically, resonance-based metasurfaces is the topic of our next lecture. Okay, so this is it for today.